Letong Wang will give the next talk, Parallel Cluster-BFS and Applications to Shortest Paths.
Yeah. Hello, everyone. I'm Letong. I'm a research fellow of the Algorithm Foundation program here, and I will become a professor at DePaul University in January. And today I will talk about Parallel Cluster-BFS and Applications to Shortest Path. This is a joint work with Yan and Guy Vellock. Yeah, and this work was first published on LNX 2025. Breadth-first search is one of the most important graph processing subroutines. It is used to computing unweighted distances, and many applications may require running BFS from multiple sources, such as computing all pairs shortest paths and computing distance oracles for first shortest distance query. And the special variant of multi-source BFS is Cluster-BFS, which is short for CBFS. As the name suggests, Cluster-BFS conducts BFS from a cluster simultaneously. So what's a cluster? A cluster is a subset of vertices that are close to each other. We use the parameter k to represent the size of the cluster, to describing how large it is, and the parameter d to represent the diameter of the cluster, describing how close they are to each other. And in this example, we choose 1, 2, 3, and 4 as a cluster. And in this case, k is equal to 4, obviously, and d is equal to 2, because the distance between any pair of the vertices in the cluster is no more than 2. If we run BFS from the sources independently, we can get 4 independent BFS trees. But if we run a cluster BFS from them, we can get a merged tree. What does that mean? Suppose, let's look at it. The first 3 BFS tree reach vertex 6 at the same round. That means that the first 3 BFS tree can be merged at vertex 6 at the same level. And to distinguish which BFS reach it, we can assign each BFS a bit vector and use a bit and use a bit vector to record this information. Record that in a single source BFS, we use a Boolean value to record whether a vertex has been visited or not. Now it's like we use a bit array to record this information for the BFS from a cluster. And the final merged tree looks like this. The color of each node indicating which BFS it is in. And let's look at the vertex 6 at level 1 again. Note that the first 3 BFS merged here. And when the vertex 6 explores its neighbors, it only needs to do so once instead of 3 separate traversals. And this can be viewed as a special form of parallelism, and we call it bitwise parallelism, because 3-edge traversal can be done simultaneously through bitwise operations instead of 3 separate traversals. And note that the achievement of this parallelism does not depend on the parallel hardware. Even running on a single core machine, you can still get this parallelism. And any questions so far? Sorry?
You will also have node 6 on the second level.
Yes, we also 6. Yeah, that's a good point. Note that in the normal single source BFS, one node will only appear in the tree for once. But for the multiple source BFS, it's a merged tree. It will appear as it may appear multiple times because it appears in different levels of the original BFS.
What's the final representation of this? Like when you draw that picture, you mean that each of those nodes is represented by one of these bitwise arrays of size k? Is that?
Oh yeah. How to represent this multi-source BFS tree? That's a very good question. Yeah. We actually after this work, we designed a general representation of this one. The way we represent it, we record the frontier, which means the nodes at each round, and also each node record its corresponding BFS label, which can be represented by a bit vector.
Can a node appear more than once on the same level?
Sorry?
Can a node appear more than once on the same level? Is that?
Oh yeah, if that is the case, we will merge it. We will only, like the first 3 BFS, it's always a 6 at the same level, so we merge it. Is that what you mean?
So they, if you appear on the same level, you always have the same, right? If you merge two nodes, they have to have the same subtree beneath them, right? Mm-hmm. So.
Oh,
So is that true that if a node appears in two trees at level k, then
all the subtrees will
all
merge.
the subtrees are the same? Is that true?
Not necessarily. Yeah, because you can see the vertices, although the three nodes, three BFS all visit 6 at this level, but later the label will be different. The subtree of
I
C.
see.
Yeah, I will show an example
I
later.
see, so you're encoding that and
Yeah.
coloring.
And bitwise parallelism shows efficiency in cluster BFS both in theory and practice. In theory, Chen's algorithm used this idea to design an all-pair shortest path algorithm and sieve the work by a log n factor. But it does not have an implementation. And in practice, Akibas and others implemented cluster BFS and applied it in a distance oracle algorithm. And we refer to this algorithm as AIY. But they only consider the star-shaped clusters, which is constructed by a center vertex and its neighbors. And both of these work focus on the sequential setting. So how about in parallel? In parallel setting, the single-source parallel BFS is one of the most well-studied parallel algorithms. And the state-of-the-art parallel algorithm solution has been fully optimized. But surprisingly, we know of no prior work that combining both bitwise and thread-level parallelism. And our parallel cluster BFS is the first one that combines both bit-level and thread-level parallelism. And we support general clusters rather than star-shaped ones. And our algorithm has theoretical guarantees, has efficient implementation, and fully optimized using the known optimization in parallel BFS. And also we find a very interesting application on shortest paths that can benefit from this algorithm. Cluster BFS is a special variant of multi-source BFS. A natural question is, why focus on cluster? What advantages can a cluster offer rather than a set of general sources? One reason is that it can save space for the distance representation. In this example, the distance between vertex 7 and the sources are listed here. And the straightforward way to represent the distances is to store them separately, as shown in the table. And according to the triangle inequality, of the distance between two vertices S1 and S2 is d. Then for another distance, such as 7, the distance from 7 to them can differ by at most d. And we can further extend it from two vertices to a cluster. If the cluster has diameter d, which means any pair of the vertices within this cluster is no more than d. And if we use delta v to store the smallest distance from v to any vertices in the cluster, and accordingly, the distance between, in this case, delta 7 is 1. And accordingly, the distance between 7 and any sources in the cluster must be no larger than 1 plus d, which is 3. And since there are only 3 cases for the distances, we can classify the sources according to their distance. For example, the set of distance 1 only contains the vertex 4, and the set of distance 2 contains the source 3 and 2. The vertex 1, and the distance of 3 contains vertices 2 and 3. And we can use a bit vector to represent each subset. And in summary, for each vertex v, we store delta v and the d plus 1 bit vectors to represent the distances. And let's compare these two distance representation. Suppose we use one word to store the distance value. And we will need k over w word for each bit vector, where k is the size of the cluster and w is the number of bits in a word. And in order that, and a machine word must be at least log n in order to store a pointer. So w is omega log n. And the normal way to store the distance takes k words to store the distance to all the k sources. And the bit compression way takes these words. And know that in reality, d is usually a very small constant, such as 2. and W is omega log n. This means we can roughly save the space by a log n factor. Any questions? Okay, the cluster distance representation is also studied in previous work, and next I will present our algorithm to see how we combine the bitwise parallelism with thread-level parallelism. Let's continue to see how 7 propagate the BFS information to its neighbors. Imagine the sources 1 and 4 have already visited 7 before the current round. And because 7 and 8 are neighbors, 1 and 4 can visit 8 after the current round. And notice that some other sources, such as 1 and 3, may have already visited 8 in previous rounds. So by excluding such sources like 1 and 3, we can get the sources that exactly visit 8 in this round for the first time. And in our algorithm, we use a Boolean array as seen to store the sources that had visited V before the current round, and as next to store the sources that can visit V after the current round. And when processing an edge, such as 7 to 8, we will propagate the S-syn of 7 to the S-next of 8, because the sources that can visit 7 before the current round that can visit 8 after this round. And note that the set operations, such as union and set minus, are implemented by bitwise operations. And all the vertices in the frontier can visit their neighbors in parallel. And because multiple threads may update the same value, we use the atomic operation to guarantee the correctness. And know that the S-next of 8 may contain some pre-visited sources. So subtracting S-syn from S-next, we can get the sources that exactly visit 8 in the current round. And these updates for each frontier vertex can also be done in parallel. And this is the overview of our algorithm. It's very simple, yeah. Next, let's see one optimization we use. The directional optimization is widely used in parallel BFS, and our algorithm can also benefit from it. The previous example shows what is a forward traversal. It means that all the vertices in the frontier can visit their neighbors in parallel and put new visited neighbors to the next frontier. And the backward traversal, on the other hand, means that all the vertices will look at its neighbors. For example, the vertex 7 will look at its neighbors 8, 4, and 9. And if any of its neighbors is in the current frontier, 7 will put itself to the next frontier. And when the frontier size is large, applying backward traversal can avoid atomic operations, and it is also more I/O efficient, so the performance is better. And the backward traversal technique can also be applied in our Cluster-BFS. Now let's look at the theoretical guarantees of the parallel Cluster-BFS.
So in the forward-backward one, which you talked about just before you spoke, and that was used before to accelerate breadth-first search, but one of the reasons it went a lot faster was that you didn't have to visit all the vertices on the backward one. As soon as you found a path, you were done. Is that true here too?
Yeah, that's a very good question. If it is a single source BFS, whenever you find one neighbor is in the current frontier, you can terminate and skip the rest. But here we cannot do that. Yeah, this is the one benefit that we cannot take from the backward traversal.
But the number of edges in the backward step, if the frontier is really large, I think it could still be much less than if you did all the out edges in the current frontier, right? Because a lot of the out edges of the current frontier could be kind of going internally within the frontier, and they're sort of wasted. Is that right?
Yes, but in the experiment we can show that, such as on the 96 core machine, if the graph is very dense, it can have even more than 96 times speed up. I think that's the reason, because it skips some edges. But that benefits cannot be taken in the Cluster-BFS. Yeah. Yeah, we use the work span model for the parallel Cluster-BFS, where the work is the total number of operations and the span is the longest dependency chain. The work of Cluster-BFS is dm times k over w plus 1. And here, D and K is the diameter and the size of the cluster, and M is the number of edges, and W is the number of bits in a word. And it is the same as the best sequential algorithm that presented in Chan's algorithm. So it is work efficient. And the span of the parallel cluster BFS is D times log n, where D is the diameter of the graph, and n is the number of vertices. And it is the same as the single source parallel BFS. And let's imagine that if you choose a cluster with size W, or say log n, and they are very close to each other, which means the D is a very small constant, such as 2. In that way, the work will become order of m, and in this way, both the work and span is exactly the same as the single source parallel BFS. The takeaway is that we can get the result of order of log n BFS from order of log n more sources, but with almost the same cost. So what applications can benefit from this parallel cluster BFS? We find a very interesting application that can benefit from this algorithm. It is a proximate distance oracle algorithm that for unweighted distances. The distance oracle is based on the landmark labeling idea. The idea is very simple. It selects a subset of vertices as landmarks and compute the distance from the landmarks to the vertices. For example, we select 1, 6, and 7 as landmarks and pre-compute their distances to all the vertices and store in the table. When answering the query for the shortest distance between two vertices u and v, such as 2 and 9, we will compute the shortest distance going through any landmarks and take the minimum one as the result. As we can see, the query will give an approximate of the distance, the shortest distance. And the accuracy of the query will depend on how close the landmarks are to the true shortest paths. Intuitively, the more landmarks we select, the more accuracy the distance oracle will be. And we design a new landmark labeling algorithm based on Cluster-BFS that instead of selecting a single vertex as a landmark, we select a cluster as a landmark and pre-compute their distances. For example, suppose we choose the vertex 1, 4, 5, and 6 as a cluster and pre-compute its distances. And when answering the query, we will find the minimum distance between u and v going through any sources in the cluster. If there are many clusters, we will take the minimum one as the answer. And due to the space efficiency of the cluster system representation, our algorithm can select more landmarks than the normal landmark labeling with the same index size. And this often leads to better accuracy than the original landmark labeling. And I will show more details in the experiment session. Any questions so far?
So if I understand, you're doing roughly as many clusters as you would have done landmarks before, but now you have more vertices in some sense because you got everything in the cluster?
Yes, yes.
Okay.
Yeah. Next, let's look at the experiment results. We did our experiment on a machine with 96 cores and 1.5 terabyte of memory. We tested on 18 undirected graphs, which are either social or web graphs with low diameters. First, let's look at the micro benchmark of Cluster-BFS. We select 10 random clusters of size 64 and diameter 2 on each graph and took the average results, which means on each graph, we tested the BFS from 640 sources in total. And our baseline, including the standard sequential single source BFS. And we compare other baselines against it to show the speed up over it. And higher is better. And AIY is a sequential cluster BFS baseline. The way we tested it, we run 10 different clusters one by one. It only has bitwise parallelism. And as the blue bar shows, it has about 20 to 30 times speed up. It's quite uniform on different graphs. Each bar represents a graph, and the last one is a geomean of all the graphs. And Ligra is a parallel single source BFS implementation. We tested 600 BFS, each one in parallel, but one by one. And we can see the speed up is ranges from 4 on the very small graphs to more than 188. Note that the machine only have 92 cores. It has the speed up is more than the number of cores because the backward optimization. Yeah. And our algorithm, shown as the yellow bar, it combines the benefits of both bitwise and thread level parallelism. And it has a dramatic improvement with speed up ranging from -4 times to over 1,000 times. This is a summary figure of the previous speed up. The numbers are the geomean on 18 graphs. Our algorithm gets 500 times speed up on average, and this speed up is nearly the product of the speed up given by the other individual techniques. And this shows that the bitwise and thread level parallelism combines very well in our algorithm. Each method still contributes almost fully to the performance. And it is important to show the scalability for parallel algorithms. In this figure, the x-axis is a number of cores, and the y-axis is the speed up, self-speed up. And we can see we have almost linear self-speed up as the number of cores increases. And next, let's see the performance of the application. The quality of the approximate distance oracle is measured by 3 metrics: the index size, pre-processing time, and accuracy. For fair comparison, we fix the index size and compare the other two. We fix it to be about 1K bytes per vertex. What that means? It means in the normal landmark labeling, we can select 1,000 vertices as landmarks. And in the cluster landmark labeling, we can select 60 clusters, and each one with size 64. Let's first compare the pre-processing time. Each bar represents a graph, and the width of the bar represents the running time. Smaller is better. And the blue bar represents the normal landmark labeling, and the orange bar represents the cluster landmark labeling. We can see that in all the cases, cluster landmark labeling is much faster than the normal landmark labeling. That is because running 60 cluster BFS is much faster than running about 1,000 single source BFS. And now, next, let's look at the accuracy. The distortion is computed by this form, and smaller is better. The blue bar represents the distortion of the normal landmark labeling, and the orange bar represents the distortion of the cluster landmark labeling, and smaller is better. We can see that in most cases, the cluster landmark labeling has better accuracy than the normal landmark labeling, because actually we select about 3,000 vertices, but the normal landmark labeling only select about 1,000 vertices as landmarks. But on 4 graphs, the normal landmark labeling has better accuracy than ours, because although we selected more vertices, the vertices within the same cluster needs to be close to each other. They are not totally independent. And the normal landmark labeling select more independent landmarks, so they have better accuracy on these 4 graphs. In summary, by applying cluster BFS to landmark labeling, our algorithm is always faster in pre-processing time and has better accuracy in most cases. And there are some future work. One is from the algorithm side. After this work, we designed a general parallel multi-source BFS framework that's as asked. And we also use that framework to implement the normal landmark labeling in centricity, closeness, centrality. And we're looking for if there are any more applications that can benefit from this parallel BFS from multiple sources. And the other one is, can we implement it on other architectures? Like if we already constructed the distance oracle, the query of the shortest distance of 2 points is very simple. It just involves loading the index stored and doing some very simple computation. And it's quite suitable for the multi-SSD machine, as Lexman mentioned yesterday. And is there any other more architectures that may be efficient to implement it? And in summary, in this work, we present a parallel implementation for Cluster-BFS. It is the first one that combines bitwise parallelism and thread-level parallelism. And the implementation is highly efficient that both techniques still fully contribute to the performance. And we find an interesting application about distance oracles. And by applying the Cluster-BFS, the landmark labeling-based distance oracle improves the pre-processing time and the accuracy. Yeah, I'm good. Any questions?
So I'm getting some intuition for the use of the clusters. I think the density of the cluster is where you're getting the efficiency from the BFS because you expect there to be overlap in the BFS trees, essentially. But so if I choose a cluster, well, if I choose something which is not clustered, so if I choose a bunch of sources but I treat them as a cluster and they're far apart, just to make sure I understand, this degenerates into essentially just many single source BFSs all combined at the same time, right?
It will not be worse than running them independently. Yeah.
Okay, so follow-up question. So I was curious about the distance oracles. Like if we can use a cluster, but it doesn't have to be perfectly dense, right? It can be like, you have a little bit of space maybe you can play with. I don't know, have you played with that?
Yeah. In our paper, we also tested that except the cluster that has diameter 2, which is quite dense, we also tested on diameter 4 that are not as dense as that, and it has more independency. But what we find is that with the same the index size limits, choosing the dense cluster will give you better performance. The reason is that when you increase the diameter of the cluster, you will pay more for the space to store the distances. Yeah.
Can you go back like 5 or 6 slides to where you had the line graph?
Oh, which one?
There's like the line graph, you called it linear speedup, you said.
Oh, this one?
Yeah, I was curious about the one that levels off, the one that's the bottom line.
Oh.
It seems like some of them are.
Oh, you mean this line? It does not speed as the course increases. Oh, the reason is that this graph, DBLP, is the smallest graph in our graph. It's very small, like parallelism. Yeah. Any other questions?
I don't know if I have a well-formulated question here, but if you're not only concerned about the bit parallelism, but you're also just trying to exploit the fact that you're sending less data in some sense by packing things in. Like you could implement a multi-source BFS in Ligra using bit vectors probably. Do you get some speed up when you do that? Without worrying about clustering and doing the other tricks that you're doing, just trying to treat multiple BFSs at once by taking advantage of the packing in some way.
You mean that you running multiple source BFS from random sources?
Yeah,
they are not need to
thing.
be
So
in a cluster.
you don't get to do the distance packing that you're doing.
Yeah, actually, we find that if you are running it on a social network that has a very low diameter of the, usually you can have some good speed up because you can imagine because the diameter of the overall graph is not very large. There are some, there will have some different BFS will merge at some point. So in that case, it can save some edge traversals. Yeah.
Okay. Thank you.